Hello and welcome to another WJEC A-Level Physics question. This one is question 5 from June 2012's PH4 paper, and it's a kinetic theory question which nowadays is in Unit 3. We've got a canister of volume 0.025 meters cubed containing helium gas at a pressure of 3.04 times 10 to the 5 pascals and a temperature 280 Kelvin, and the relative molecular mass of helium is 4. We've got to calculate the number of moles of gas in this canister. So what we're going to do is use PV equals nRT. The rearrangement is N is PV over RT. Pressure 3.04 times 10 to the 5. Volume 0.025. R 8.31 given in a data book. Temperature 280. So if we put those figures into the calculator, we get an answer of 3.27 moles. Next we've got to find the number of helium molecules in the canister. Well, remember that 1 mole contains Avogadro's number of particles, so the total number of helium molecules is the number of moles times Avogadro's number. So we got 3.27 times 6.02 times 10 to the 23, value of Avogadro's number in the data book, and that gives us 1.97 times 10 to the 24. And no unit because it's just a number of molecules. Next we've got to find the density of the gas. Density is mass over volume. We know the volume is 0.025 meters cubed. We know that there are 3.27 moles, and the fact that the MR is 4 tells us that the mass of 1 mole is 4 grams, which we need to work in kilograms. It also tells us the mass of 1 molecule is 4 U's. Put those figures into the calculator, gives us 0.523 kilograms per meter cubed. Then we've got to find the RMS speed of the molecules. Well, in the data book we have the relationship that P is 1/3 rho c squared bar. So the root mean square speed is going to be the square root of 3 times the pressure over the density. So it's a square root of 3 times 3.04 times 10 to the 5 over the density that we just calculated. And putting that into a calculator gives us about 1320 meters per second. And that's a sensible answer. Most gas molecules have RMS speeds of around a few hundred meters per second at normal pressures and temperatures, but helium and hydrogen, being lighter molecules, tend to have higher RMS speeds, so this makes sense. For part B of the question, we're given 2 equations which show the product of the pressure and the volume of an ideal gas. We have PV equals nRT that we used earlier in the question, and also PV is 1/3 nmc squared bar. And we've got to derive in clear steps a formula that shows how the internal energy of the ideal gas depends on the temperature of the gas. Well, we need to know that the internal energy U is the total kinetic energy of all the molecules. To do this derivation, we're going to start by saying that PV is nRT and PV is also 1/3 nmc squared bar. So we can equate nRT to 1/3 nmc squared bar. If we look at the right hand side of the equation, it's almost what we want for U. N is the total number of molecules and kinetic energy is a half mc squared. So if we can get rid of the third and turn it into half, then the right hand side will actually be U. So what we're going to do is we're going to multiply both sides by 3/2. So the left hand side will become 3/2 nRT, and the right hand side, well, 3/2 times 1/3 times nmc squared bar. We'll see that those cancel, and let's rewrite the right hand side in a slightly different way and write it as n times a half mc squared bar. Well, n is the total number of molecules. Half mc squared bar is the mean kinetic energy of 1 molecule, so the right hand side is the total kinetic energy of all the molecules. So we've derived this expression that U is equal to 3/2 nRT. And that's a standard derivation that comes up fairly regularly. Next, we've got to calculate the internal energy of the helium gas in the container. So we can use 3 over 2 nRT, because we know the number of moles, we know R, and we know the temperature. I'll show you another way in a second, but let's calculate that first of all. So it's 3 over 2 times N. If we go way back to the start of the question, N was 3.27 moles. R is 8.31. And the temperature was 280, I think. Yes, 280 Kelvin. So I'll put those into the calculator, and we come up with an answer of 11,400 joules. Now, a quicker way of doing that is to remember that PV is equal to nRT. We've got that up here. So we could also, so let's put this as an OR, we could also have used the equation U is equal to 3 over 2 PV. Remember, nRT is PV. So 3 over 2 times the pressure, which I think was 3.04 times 10 to the 5. Times the volume, which was 0.025. And that will give exactly the same answer, must do, of 11,400 joules. That trick that U is 3 over 2 PV can make quite a few questions a lot quicker to do. So, thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.